Okay, so now that Lee has a basic project set up that we can use to test out various types of noise, in this video we're going to start focusing on value noise. And specifically with this video, we're going to be taking a look at the theory behind value noise. Lee?
Right. So we're going to start off with one of my little favorite tools.
Which I
If I
need
can,
to, yeah,
yep,
hang on.
if you can help.
There you go.
Yep. Now, actually, I wanted to bring up Firefox so they could see this in case anybody else wants to go to it. This little website, Graph Series Math Study.com, has this nice little Java applet that pops up when you go to the site, which looks like this, and it's a cool little graphing program. What I've got it graphing right now is just a simple sine wave. I'm going between a -1 and 10 on X and a min and max of up to 10 on my vertical. So this just is a very simple sine wave. Now, what value noise is in essence a noise wave, just like a sine wave, but instead of having our high and low points of our wave at a set interval along the noise wave, these vary. So they're picked at random. Based on some value of X, we get a value back. Now, this is assuming that we've got a 1D noise. So where X is our one dimension, we feed that into our generator, we get one number back. Now, what value noise does is it smoothly interpolates between each one of those points and tries to give us a nice wave back. And we use that into whatever we want to add noise to. Now, what I was mentioning before is usually noise programs work by sampling multiple times at different frequencies at different amplitudes and then blending all that in to get a final noise. Now, this is not a noise curve in itself, it's a sine curve, but I can demonstrate the effect by using a sine wave. So if I take the sine wave and I multiply it by 4, regraph it just to make it a little bit easier to see, get a little bit more amplitude out of it. Now, if I take this same sine wave, copy it, and then to it, I add another sine wave, but I take its frequency and I multiply it by 2. So I'm doubling its frequency and I have its amplitude.
Half is,
Yeah.
okay.
4, half is
Oh,
amplitude
half
is
is in
2.
that. Yeah.
Okay, well, it is almost 4. So
Yeah, I'm just used to when I'm seeing numbers half, times 0.5.
yeah,
Continue.
but
Yeah,
we
I'm with you.
started off with 4.
Yeah.
So now, as you can see, our sine wave has modified a little bit.
Hmm.
Now, if we keep this process up, so I take this again, and this time we will take just X as it is with no amplification. We add it again. So, well, half of 2 is 1 and multiply. So now it's modifying it, but not a whole lot. We do it again. This time, well, hold on. I was doubling. I forgot to double. Let me do this. Take this iteration off because I'm doubling frequency each time. I forgot to double the frequency. So now frequency is up by 4. Half of 2 is 1, so I'm not going to multiply by 1. Graph it. Now we get a little bit more noise in here. Paste it again. This time 0.5. There's your half.
Yay!
And we double the frequency again, which goes up to 8. We graph this, and we'll do it one more time. So this will take us to a frequency of X times 16 and 0.25 for our amplitude. So now we start seeing some noise. Now there's definitely a repeating pattern here that you can see. And with a noise wave, when you're starting out with something other than a sine wave, this becomes much more difficult to see. Now this would be a 1D type noise, because we're only feeding in an X and we're getting a Y. Even though this is a 2D graph, it still would be considered a 1D type noise. Now, I can duplicate all of this, and let's add this to itself. But in here, everywhere where I had X, if I go ahead and change it to Y, change our min and maxes to 10. I'm going to copy and paste this or copy it just in case when I change this, things blow up. Yeah, like that.
Very good.
And I regraph it. Now it's kind of hard to see because of the way it's shaded. Let's see, if I take all of this and divide it by 4. There we go. Something a little bit easier to see.
Mm-hmm.
But now while it's a 3-dimensional shape, we've in essence created it with a 2D noise, because we're taking input on X and Y, layering it in multiple passes. We're actually doing 5 passes, I believe now. So X, 2, 4, 8, and 16. So we're doing 5 different passes of sampling in both X and the Y axis, which is returning a value at some point in Z, which gives us our 3rd dimension. So we're using a 2D noise, simulated noise, to, in effect, make a 3-dimensional height map. I don't know. Could you think of any uses that might be useful for?
No clue at all.
Yeah, maybe like terrain. But just something that if you wanted to do it. And this is why I said we don't really need a 4-dimensional noise in our instance, because if we wanted to animate this over time, then our 3rd dimension would give us the ability to do that. We wouldn't have to do this over a true 4-dimensional shape.
Mm-hmm.
So that is the basic theory of what we're going to be shooting for. Now, I want to go ahead and close this out. And I'm going to close this one out. Now, we're going to come back to this site in just a sec. The way I stumbled across value noise was because not a whole lot of people know about value noise. Most people know about Perlin noise because it is probably the most popular, catchphrase out there when you're searching for noise. So just like most people who are looking for information, I went to Google and I typed in Perlin noise. Now, in Chrome on my computer, the very first site that came up, even before the wiki, was this site called Perlin Noise. So I clicked on it, and it's like going, oh, great. So this is Perlin Noise. So I started reading, and if you look, it's talking about how you can take a random number and plot it based off of X and get some random number from 0 to 1 along the Y-axis, kind of like what I was discussing with the sine wave graph. And then what it does is it tries to smoothly interpolate between all those points and returns a noise curve, kind of like this. So what they do is you take that noise curve at some amplitude and some frequency, and you combine it with another curve and another curve and another curve, and you keep going as many times as you want. And when you add them up, you get this really nice noisy curve. And then you get something like this. This is where I was talking about you do one curve with one set of numbers, and you generate something like this. Then you double the frequency, reduce the amplitude in each octave, and then when you combine them together, you get something that looks really nice. Now, I was like, oh, great. And I kept reading and I implemented this. And then I realized that after a while that reading other papers about Perlin noise, they didn't sound anything like what was described in this paper. So I started doing some more research. Turns out, while this is a very good explanation of how to do noise, this is a very, very good explanation on how to do value noise. This is not Perlin noise. So anybody who's gone here and implemented this, this is really not Perlin noise. And you may have seen it because further down, this is where I came up with the random noise generator. That's not a random noise generator either. But it's a definitely good site for Perlin. And actually, I think...
For Perlin?
Or, sorry, yeah, it got me confused again.
Value.
For value noise. But it's a really good resource on value noise. And I want to see if I can find it, because I did a search when I was trying to figure out if anybody else realized that that wasn't the traditional Perlin noise.
Mm-hmm.
And I want to see if I can find... it's Hugo Elias, I think. And
Down, is that, yeah, in there possibly?
yeah, I think this is the one. Yeah, here you go. So it's just basically, this is value noise, not gradient noise, aka Perlin noise. And then it goes on. It's basically, it was talking that Ken Perlin himself has actually acknowledged that it's a good website on value noise, but not his Perlin noise. So,
Okay.
but like the basic is, it's not a rubbish site. It's just not Perlin noise. But definitely give this a read over, because
Is there anything that you can cover here in regards to the theory of value noise?
we're going to.
Okay.
I'm just saying, I'm just going to give a short overview of what's going on,
Mm-hmm.
and then we will go more in depth as I start coding it. But definitely come in here and read this, just for a separate perspective. Now, the way we're going to implement this is we're going to need a random number generator to get our information for our points, which are basically here. So what we're going to be trying to do is generate points for our noise curve. Luckily, I seem to think we've already gotten random number generation pretty much squared away.
Mm-hmm.
So we don't have to worry about that. What we do need to work on is to smoothly interpolate these points into a nice little curve. So we're going to be looking at ways of smoothing out the information. Now, to do that, we're going to be using what is known as smooth noise. And that's covered in this part of the article. In essence, what we're going to be doing is taking our 2D noise and sampling based off of our X and Y positions. If you think of it like a sheet of paper that has four corners on it, we're going to be taking the corners of each of those or each of those points on a sheet of paper, those corners, getting the noise returned from our noise or our 2D hash at each one of those points, averaging those together or adding those together, dividing them by 16, and then doing the same thing again with the sides, which are the points that are directly in the middle of each side of the piece of paper, getting those points, adding those together, dividing them by 8, and then taking the noise that we sample at the very center and dividing that by 4. We add all 3 of those together, and that will return us a nice smooth number for our noise. And if we go back here and we run this again, as you can see, we've got lots of different points in here, but none of this is very smooth as far as gradients. So what we're doing is, if I pause this so it doesn't update, we'll be taking a point and going, let's say this point on this corner right here. We're going to take its color, and we're going to take the color at this corner, and the color at the lower right corner, and the color at the lower left, taking those 4, adding them together, dividing them by 16. Then we're going to take the color in the middle up here, and the middle on the right, the middle on the bottom, and the middle on the left, adding those together, dividing them by 8, and then taking the color in the very center and then dividing that by 4. And then we take all of those samples, add those together, and that will be our return sample color. So what we're doing, sampling multiple places and in effect smoothing it out. Now once we've done that, we use multiple points. Wrong window. We're going to take those multiple points and we're going to be blending between them. So if I scroll down to our interpolated noise, so we've got smooth noise, so we're going to take a sampling across that texture that I just showed you inside of Unity. We're going to take each one of those points that have been smooth, and we're going to interpolate between each of our points to get a nice smooth curve between our already smooth noise. So if you look where we've got our smooth noise here, we're going to get our value. This is our values that we're smoothing up above. We're going to get 4 of those, 1 for each of our corners, and then we're going to take the top 2 corner, or let's see, in this case this is V1, V2, which is the this would be like the upper left corner, and V2, which is the upper right corner. We're going to blend those together by a fractional amount and do the same thing with the lower 2 corners. Then we take the result of those 2 and blend those together. And this is all the calculations are going on for just a 2D. 3D gets even more complicated because we've got to do the same thing, but we also have to take into consideration the z-axis. So we actually have 8 different combinations of these, 4 different combinations of these, and then we've got 2 combinations of this blend, and then another combination of the result of those 2. And they cascades, and we'll go through that in the implementation to make sure that you understand. But what we're doing is we're sampling all over the place, blending it down to try to make a very smooth gradient, which is one of the things why true Perlin noise is superior to value noise in a lot of ways, because it comes with a pre-calculated gradient that we can use that is just rotated, so we don't have to do all these smooth samplings and then smooth blendings between them and then blend those down and blend those all the way down. So hopefully I can make that a little bit more apparent as we start coding the program itself, or that part of the class itself.
Cool.
So, but like I said, if you want to look at this site, definitely give this one a look over. It's got some really cool things, especially when you start looking at the cloud article and some of the different textures that you can use by different applications of the noise itself. So,
Very
but
nice.
the big things that take away from it is this is value noise, not Perlin. and it is expensive, extremely expensive as
Okay.
far as computational overhead.
Okay. Well, is that pretty much everything that you wanted to cover here?
Yeah, as far as what I can get into without actually starting to throw up some lines of code.
Right. Okay. Well, with that, then we will go ahead and wrap up this video and move over into some implementation. So thanks a lot, everyone.